Hello everyone, in this video we're going to be discussing centripetal force. We're going to be deriving max speed around a curve, minimum speed to get through a loop, and some really challenging problems. This can be a really difficult topic, so make sure you watch through to the end, as you'll pretty much be able to solve any centripetal force problem, except for maybe some satellite problems which we'll talk about in part 3 in the next video, so stay tuned for that. Alright, so what is a centripetal force? So simply, the centripetal force is just the net force when there's a circle involved. So if an object is making a circle, the net force is the centripetal force. So it's not a new force. So we know the net force just equals the mass times acceleration, but in this case the acceleration is the centripetal acceleration. So we learned last video that the centripetal acceleration is just v squared over r. So if we plug this into this equation, we get mv squared over r is the centripetal force. And if we want to derive these two equations using frequency or the period, we could use the equation for centripetal force with mv squared over r, and we could simply plug in the tangential speed equation, which is 2 pi r over t. If we were to plug this in up here, we would get this equation, and we could plug in 1 over frequency equals the period to get this equation. So I want you to not try to memorize these equations, but simply just understand where they're coming from. It's just a net force. It's not a new force that's added. And so we can derive the equation just as we treat any net force as mass times acceleration. Alright, so let's do a simple example to start off here. So we have a ball attached to a string is rotated on a frictionless table. The mass of the ball is 5 kilograms, the linear speed is 4 meters per second, and the radius of the circle that the ball makes is 2 meters. What is the tension in the string? Okay, so let's draw a little picture for what's happening. So let's give like a top-down view of the table here. So we have a ball that is being spun in a circle basically by a string. So it's going around like this in a circle, and a string is attached to it. So at any point, if this is the top view, if we were to look at the horizontal and draw the free body diagram, the ball obviously has some force due to gravity and some normal force from the table, and so these will equal, but then it will also have some tension. So if I were to draw it at, let's say, like this point here, the tension would obviously be pointing towards this direction, and so this is force due to tension. And so this tension force is always going to be pointed towards the middle of the circle, because the string is always coming from the middle. And as we learned with centripetal acceleration, it's also in the same direction, which makes sense because the force and the acceleration are going to be in the same direction. Okay, so we could make our balance for the y direction, but that's not really going to help us out because we just know these two forces here are balanced. But if we look at the x direction, we know that the force net is equal to this Ft, and we know it won't be 0 because this force is changing because it's changing direction. But what is this F net? Well, since it's moving in a circle, the net force is just going to be the centripetal force. So the centripetal force is equal to this force tension. So you may hear that this tension is what's causing the centripetal force. And in this case, they're going to just be equal to each other. So I forgot to do this, but we should list out what we actually are given here. So we know we have the mass of the ball, which is 5 kilograms. We have the linear speed, which is 4 meters per second. And we have the radius, which is 2 meters. And so if we go ahead and see what we know what the centripetal force equals, is just mass, speed, or tangential velocity squared over r. And that's going to equal our force tension. And we have all these variables. These were all given. So now we can just simply plug these into the equation and solve for our centripetal force, which if we plug that into a calculator, we would get about 40 newtons. Okay. Now let's apply this to find the max speed on a flat curve. So basically what we're trying to find here is if a car is traveling around a curve, what is the max speed that it can travel, given certain parameters. So the parameters that we're going to be allowed to use in this equation is the coefficient of friction, the gravity, and the radius of the curve. So you would have to know this, but this might be a formula that you can use for some word problems, but I'll go ahead and derive the equation and show how this is made. So let's do a little picture of what this will look like. So let's say we have a curve here, like this. This is like a road, right? And so there's a car that's traveling around this curve like this. So we want to know, given the radius of the curve and the coefficient of friction, which we'll see is static, and I'll show why it's static, what is the max speed that this car can travel, because it's traveling with some velocity. So how are we going to figure this out? Well, let's go ahead and draw our free body diagram. So our free body diagram, I'll just do for like any position, is obviously going to have gravity and the normal force, which these are equal. And then it's also going to have some force that's keeping it in. So we know that there has to be some centripetal force, some force that's causing this centripetal force that's causing this car to move this way and not slide out. And you may think it might be like applied force or something because the car is turning, but really what's happening is friction is keeping this car from sliding out this way. So this force here is actually going to be the frictional force. And so this force on the x direction is going to be force due to friction. Or that should be F. So this is force due to friction. But the reason we're going to say this is a static force is because even though the car is moving, it's not sliding, it's rolling. So when a car's wheel is rolling on the ground, each point is still statically contacting the ground as it rolls. It's not sliding directly forward. So that's why we use a static friction. And we need to know the max speed that this static friction can hold the car in place. So if we do our equation in the x direction, right, we know there's going to be the net force equal to this force due to friction. And because this car is traveling along a curve, we can say that this net force is Fc, force due to friction. And so we have an equation for Fc, and we also have an equation for F for friction. So we know the centripetal force is mass velocity squared over r, and the friction is the coefficient of static friction times the normal force. And so now we need to know what this normal force equals, because we don't really want normal force in our equation. But if we go back to the y direction here, we know that Fg equals Fn, because the car is not accelerating in the vertical direction, there's no other forces. So if Fn is equal to Fg, we know Fg equals mass times acceleration, which it's the mass times acceleration due to gravity, so it's mg. So we can plug in mg here, and if we plug all these in, we get mass velocity squared over r equals the coefficient of static friction, mass times gravity. And so now the mass will cancel out. And now we can solve for our max speed here. And if we want to solve it for just v, we take the square root. And so this would be our max speed equation. And notice that it's independent of the mass. So no matter how heavy the car is, it doesn't impact the max speed it can travel. Which might kind of sound like counterintuitive, but if you think of like a big truck, it's not that it's going to slide out easier, it just might tip over, which is a whole different scenario. This is just looking at the max speed it can travel before it slides out. Alright, now let's do a very difficult question here. So we have a ball with a mass swings from a string of length L as shown below. So this should have length L. The ball makes a horizontal circle with a radius r, and the string makes an angle theta with the vertical. Derive an expression for the speed v with these variables. Only L, g, and theta are allowed to be in our equation. Okay, so we know this ball is traveling with some speed and it has some mass. So we can just say, yep, it says the ball of mass m, so we'll say this ball right here has mass m, And so we know it's traveling with some speed v, and we want to see what this speed v is in terms of L, G, and theta. Okay, so how are we even going to start this? We'll start this just as we do any other equation. We'll list what we know, which is kind of all taken within this picture. We know the angle, L, V, M, and R, and we know these are the variables that we're allowed to use. So let's draw our force diagram. So we'll draw it at this position even though we know it's rotating around. So at this point here, there's going to be some tension force that comes up like this, and that's the force due to tension, and the force due to gravity. And that's it. That's the only two things acting on this ball is gravity and this string here. And so we can break up this tension force into its x and y components. So this is Ftx and Fty. And we know that Fty and Fg must be equal since they're the only two forces, and this ball is not accelerating in the y direction. Alright, so let's break out our x and y force equations. So in the x direction, we have the net force is equal to Ftx, and that's all we really have here. But we know what the net force equals in this case. Because it's moving in a circle, we can think about this is a horizontal circle. So it's moving in the circle in the horizontal direction. This net force is just the centripetal force is equal to Ftx. And then we can go ahead and break up these into their what these forces equal. So we know the centripetal force is mass times velocity squared over r. And then Ftx we know is going to be Ft times either cosine or sine theta. But this will be a little bit tricky because since this theta is off the horizontal or off the vertical, it's going to actually be sine theta here. And that's because if we were to draw this as a separate triangle like this, this is our theta and this is our Ftx. So this is opposite over the hypotenuse. So usually we have the angle on the horizontal, which means the x direction is usually cosine, but in this case it's sine because it's off the vertical. So that's something to make sure, and don't just automatically put cosine when you see x. Okay, so there's our x forces. And so we can't really get rid of this Ft yet because we don't know what Ft equals. Like, we have it equaling to all these things, but there's still a lot of variables that we need to get rid of, like the radius and stuff like that. So let's just write out our y direction to get some more information. So we have in the y direction, we already said that this Ft in the y equals Fg because the net force is 0. So we can say Fty equals the Fg. And so we can break up this Fty just like we did the x, and then this times it will be cosine theta, and Fg will be mass times gravity. Okay, so what are the two variables that relate these two equations? Well, the tension relates these two. These both have tension, and we can't really do anything with tension. So let's try setting these two equal to tension. So if we find that the force tension equals, we can divide this sine theta over, and we get sine theta times r. And then on this side, if we divide the cosine theta, we get Ft equals mg over cosine of theta. So now we have two things that the Ft equals, so we can set these two equal to each other. I'm just going to scroll down for some more space here. So we can now say that mv squared over r sine theta is equal to mg over cosine of theta. So right away we can go ahead and remove these masses because those cancel out. And we can, so we can move those over, and then, okay, let's rewrite our equation. So we have v squared over r sine theta equals g over cosine of theta. So what are we allowed to have in this final equation? So we can only have L, G, and theta, but we have, and we're trying to solve for v, but we still have this r. So how are we going to get rid of this r? Now the way we can get rid of this r is actually using this triangle we have up here. Because if I rewrite this triangle again, we have r, because this is the radius, this is the length of L, the string, and our theta is right here. So if we go ahead and write this as sine of theta is equal to opposite over hypotenuse, which is r over L, we can solve for r, and so we will get r equals L sine of theta. And so now we can plug this back into our equation here, and we get v squared over L sine squared of theta, because I multiplied the sines together, equals g over cosine of theta. And now we only have L, theta, and g in our equation, and we can solve for v. So if we multiply these over, we get v squared equals g L sine squared theta over cosine of theta. And if we take the square root of both sides, we get that v equals the square root of GL sine squared theta over cosine theta. So that would be our final answer. We could also pull out the sine theta if we want to get rid of the squared inside and say GL over cosine. And this would be our final answer. So this is a really long problem with a lot of steps, but I do this just to illustrate, like, even when you don't really know what to do, just start by taking the steps we always take in a physics problem, like identify what variables we have, what we need in our final equation, draw our free body diagram, write our x and y, and see what you can set equal to each other, see what cancels, and see what other relationships, like a triangle here or a circle, that you can use to solve for these other variables. Alright, so we're going to do one other example where we derive the equation for the minimum speed around a vertical circle. So this is pretty common, like question. You might want to like have this equation memorized, but I'm going to derive what this is kind of saying. So let me scroll down. So we have a vertical circle. So let's say we either have like a string with a ball that is like making a circle here. And so let's say this ball is being like flung around in a circle, or maybe you have like a roller coaster loop, and so there's a cart that's on this loop here. And so, you know, like if you're swinging a ball, there's going to be some speed where it stays up and keeps a circle. Or if you like use like a Hot Wheels car, go around a loop, there's some speed that keeps this car to the loop. So what is it that it's keeping this keeping the ball in the loop or the cart in the loop? And so in both these cases, the centripetal force. So at each point, there's some centripetal force that is causing this ball to stay in the loop, or there's some centripetal force that keeps the cart in the loop. Okay. And so in this case, the centripetal force is simply just the force due to tension on the string. And in this case, the centripetal force is equal to the normal force. But there's also going to be another force in play, and that's gravity. So let's look at this position right here. I'll just do it for this scenario. I'll do this in green. I'll do it for this scenario, but this could be applied to a track as well. So at this point at the very bottom, we have some force due to gravity and some force tension. And in this case, the centripetal force is equal to force due to tension minus the force due to gravity. And so the tension will be larger than gravity, because we know the centripetal force will be in the same direction as the tension force. And that's what keeps the ball moving around. But let's say we get to point 2 in the loop. So this is point 1. So at point 2, now we have a free body diagram that looks like this. We have the force due to gravity coming down, and the force tension like this. So at this point, the centripetal force just equals the force due to tension, because it's the only force in the same direction as the centripetal force. And so this makes sense because our net force here, our net force overall, is right here, and we know that the net force is going to be pointing this way, so that does make sense. But if we're looking at the centripetal force, it'll be like right here. But let's look at this top point, and this is what we really care about, is our point 3. So at point 3, I'll scroll down a little bit here. At point 3, our free body diagram will have force due to gravity coming down, and at the same point, force tension. And so our centripetal force is going to be equal to this force tension plus force due to gravity. And so now let's say we want to find the minimum speed that this ball can be moving so that it stays in the loop. So if we wanted to have a minimum speed so that it stays in the loop, for the minimum speed, this force due to tension would be approaching 0. So this would be going to 0. So our centripetal force would end up just equaling the force due to gravity. And so now we can plug in the variables that we know here, which is the mass times velocity squared over r and mg for gravity, and these masses cancel. And now we can solve for our speed, which we see equals the square root of rg. And so this may look familiar to the max speed around a curve, but this is the minimum speed along a vertical circle. And this can be used in a lot of problems, but you should understand how you can derive this equation so that you find the minimum speed. Because if you go faster, it'll still stay in the loop, but if you go any slower, it's going to, say, like reach the top of the loop and then fall. So like if you have a cart here and it's moving and it's trying to get to the top, but then it runs out of speed, and in this case there would be no more normal force. I feel like it's a little bit more easy to understand. If there's no more normal force, you're not contacting the track anymore, you're going to fall down and it's just going to be gravity, and you won't have enough speed to get around. Alright, so that is all I got for this video. Stick around and watch the next video to talk about satellites and how their circular motion works, and that'll be the last part of the circular motion series. So yeah, thanks for watching.